If you haven't seen the special relativity videos yet, start there first. In 1905, a young Albert Einstein transformed physics. He showed that time can slow down, distances can shrink, and mass and energy are two forms of the same thing. Special relativity explained motion, light, and energy, but it left one enormous mystery unsolved. Gravity seemed to be everywhere. Apples fall, planets orbit, rockets accelerate, entire galaxies form because of gravity. If Einstein wanted a complete description of the universe, he would have to understand gravity. For years, he searched for an answer. Then, in 1907, Einstein had an idea he would later call the happiest thought of his life. Imagine a man falling from a rooftop. His keys fall beside him. A notebook falls beside him. Everything falls together. To someone on the ground, gravity is pulling everything downward. But to the falling man, the objects beside him appear to float. For a brief moment, gravity seems to disappear. Einstein pushed the idea further. Imagine a sealed elevator with no windows. If it sits on Earth and you drop a ball, the ball falls. But if the elevator is floating in deep space while rockets accelerate it upward, the ball still falls. Inside the elevator, every experiment gives the same answer. There is no way to tell the difference. Gravity equals acceleration. For more than 2 centuries, scientists had described gravity as a force pulling objects together. But Einstein began wondering if gravity might be something deeper. Imagine a plane flying from New York to Tokyo. The pilots follow the straightest route available, yet on a flat map, that route appears curved. That's because the Earth itself is curved. Einstein wondered whether something similar was happening in space. Maybe planets aren't being pulled by a force. Maybe they're following the straightest paths possible through a curved universe. The idea was elegant, but Einstein lacked the mathematics needed to describe curved space. He turned to his friend Marcel Grossmann. Grossmann introduced him to a branch of geometry developed decades earlier by Bernhard Riemann. After 8 years of work, Einstein finally completed a new theory. In 1915, he published General Relativity. In this new picture, matter changes the geometry of spacetime. The sun changes the shape of spacetime around it. The Earth follows the natural paths created by that geometry. Gravity is no longer a force. It becomes a consequence of the shape of the universe itself. The theory made a shocking prediction. If spacetime can curve, then light should follow those curves too. Starlight passing near the sun should bend. There was a problem. The sun is normally too bright to see nearby stars. But in 1919, astronomers had a rare opportunity. During a total solar eclipse, the moon would block the sun's light. English astronomer Arthur Eddington organized an expedition to test Einstein's prediction. When the photographs were analyzed, the stars appeared slightly shifted. Their light had bent while passing near the sun. Einstein's prediction was correct. For the first time, scientists had evidence that gravity bends light. But Einstein's equations contained an even stranger possibility. While Europe was fighting World War I, a German physicist named Karl Schwarzschild began studying Einstein's newly published theory. He discovered the first exact solution to Einstein's equations. Schwarzschild found that if enough mass is compressed into a small enough region, gravity becomes so strong that even light cannot escape. Any light trying to leave falls back. Today, we call these objects black holes. What began as a problem with gravity transformed our understanding of the universe. Einstein's search led to curved spacetime. Curved spacetime led to bending starlight, and bending starlight revealed the possibility of black holes. For decades, black holes existed only in equations. But a century later, scientists would do something even more astonishing. They would listen to 2 black holes colliding.